Hello everyone. I think since it is 7:05, maybe we can start. I'll just share my screen. Is my screen visible? Oh. I'm audible. Okay. Okay. Now is it fine? Okay. Okay. So my name is Annette Maria Teddy. I'm a PhD student in the Department of Chemistry at IIT Tirupati. So as we know, this is the third week of the problem solving session in Basics in Inorganic Chemistry course. So I'll just continue from some of the portion that we could not solve last week, which is the elegant diagram. So I'll just solve some questions based on elegant diagram. Then we will move on to crystal feed, splitting, spinels, and so on. So this is a straightforward question. This is the elegant diagram which is given for the formation of carbon dioxide. And the question is the elegant diagram for the formation of CO2 is a straight line in the given graph. This is due to these reasons. So first we will understand what we have to really look at. Okay, so I think all of you are familiar with this equation, delta G is equal to delta H minus T delta S. So for any reaction to be feasible, delta G should be negative and delta S should be positive, right? So here, and how to find out if delta S is positive? So for this reaction, I will write. So here is carbon is in the solid state, O2 is in the gaseous phase, then carbon dioxide is also in the gaseous phase. So here a solid plus gas is becoming another gas. So basically there is no change in the entropy, right? Because there in the product also there is a gas, in the reactant reactant also there is a gas, in the product also there is a gas. So there is no change in delta S. There is no change from product reactant to product that in the delta S. So definitely the entropy remains constant during carbon monoxide formation. That's why we have this. So this T delta S component is here. Since we are plotting against T, since this is same, then we will have a, since delta S is constant here, we will have a constant slope here. That's why we have a straight line in this graph. The entropy remains constant during carbon dioxide formation. So is this clear? Just delta S. But when we are looking at this delta G, that is the free energy change, we are essentially looking at this delta G is equal to delta H minus T delta S. And this diagram is also delta G versus T. So here we are getting a straight line because T delta S is a constant, right? Let me write it properly. T delta S is a constant. That is why here we are getting a straight line. So T cannot be constant because T is the variant here, variable here. So T can be any value, right? So delta S must be constant, right? So that delta S is constant because we are changing from reactant to product. There is not much change. It is a gas to gas. So the disorderness is the same. That's why there is no change in the delta S. Is it clear? Okay. Yes, T is temperature, generally in Kelvin. Yeah. Okay. So we'll move on to next question. So we select the correct statement. This is also related to the formation of metal oxide, elegant diagram node. So the options are, first we have to select the correct state. So I'll just read out the options. In the decomposition of an oxide into oxygen and gaseous metal, entropy increases. So let's just first we'll check if it is true. So decomposition of an oxide, right? So we'll just write the oxide, MO. MO is the oxide. If it is decomposing, then it should turn to M plus oxygen, right? And they have given, this is generally in solid form. and they have given that gaseous metal. So this is in gas. Oxygen, as you know, is gas. So it will be 2 R42, right? So from solid to gas, two gases are forming. So definitely entropy is increasing. So this is a right statement. Then we'll check the decomposition of an oxide is an endothermic change. So in the previous, okay, here we can see the temperature with, okay, 1 second. Here we can see that with temperature, this graph is going up, right? So it means that the option was a decomposition of, okay. Okay, so see, till 2400 degrees Celsius temperature, the oxide formation is still happening. So definitely if we need to decompose an oxide, we have to give some energy, right? Like the formation energy of oxide is this much high. So if we have to decompose the oxide, we definitely have to give energy. So endothermic means we have to give energy. Exothermic means it will release energy. So definitely this option is also right. Decomposition of an oxide is an endothermic change. So this is also right. So next one, to make delta G negative, temperature should be high enough so that T delta is greater than delta H. So for that we will just check how is it possible. So let me take delta H, delta S, delta G, which is equal to delta H minus T delta S. Let's say my delta H is 10, and we'll keep a, for now we'll keep a constant temperature of 100 Kelvin, and this is in kilojoule per mole, this is in kilojoule per Kelvin. Okay. Am I still audible or my internet connection got disconnected? Okay, okay. Yes. So right now I'm just fixing, but the elegant diagram we can see different temperature, because at each temperature, what is the delta G? That's why, that's what that graph is showing. 1 second. Give me a second. Okay, I have some internet issue. Actually, people are joining as well, so I have joined from my mobile phone also to, admit those people, but there is some internet issue. 1 second. Yeah. So whenever I am not audible, please let me know. Okay, just tell me, because sometimes I won't be looking at the chat box. Okay, so yeah. Okay, so right now I am fixing the temperature at 100 Kelvin. So let me just, arbitrarily I am saying my delta H is plus 10, that is positive 10 kilojoule per mole. And let's say my delta S is also positive and it is also plus 10. So delta G will be how much? Delta G will be 10 minus this T into 10, right? So T is 100, 100 into 10. So it's 10 minus 1000, right? So it is still a negative value, right? So when delta H and delta S are positive, delta G is negative. So that is okay. Now what if this delta H is negative and my delta S is still positive? Then delta G will be minus 10 minus 100 into 10. So minus 10 minus 1000. So it is still a negative value, right? So in both these cases, my delta G is negative, which means that my reaction is possible. So our question was, if do we need to follow uh, this condition that T delta is greater than delta H? So let me take another example. Delta H is the enthalpy of formation. Whenever a reaction is happening, how much energy is released or accepted. It's like exothermic or endothermic. So if it is endothermic, then it is generally plus. If it is exothermic, it is negative. It is shown negative. So if sometimes we have to give some energy for the reaction to happen, that's when we have this positive 10, positive delta H. When it releases energy, that is heat, when it forms or when reactions happening, that is exothermic. That's when we have this negative delta H. um okay, so oh, okay, now am I audible? Hello? Hello? Okay, 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 so maybe one participant is having issue. So so here also delta, in both these cases we can say that T delta S is greater than delta H, right? Because delta H was just 10, then T delta S is minus, T delta S is like a large value. That's how we got this delta G, right? So now, what if um, delta H is still 10 and delta S is negative? I think you are having some internet issue because other participants are able to hear. Um, like if you are not getting the concept, maybe at the end also we can discuss separately. But I think the issue is not on my side. Mm. So delta G. So in this case, delta H is positive, but the delta S is negative, right? So minus, yeah, 100 into minus 10. So it will be 10 plus, because minus minus will become plus, it will be 1000. So it is, now it is becoming a positive value. So in whenever delta S is positive, we need to have this T delta S greater than delta H condition, and whenever delta S is negative, then we have to have this delta H should be larger. For example, I can say some this 1000, right? So 1050 something, delta H is 1050, and if we calculate delta G now, it will be 1050. No, then in that case delta H should be negative. Yeah. Huh. Yes. No, this, yeah, here see, first I am substituting here delta H is, in the first case delta H is 10, then in T is 100, then this 10 is for this delta S. This is the first case. Second case, my delta H is minus 10, so I have given minus 10 here. Then T is still 100, my delta S is positive, so 10, positive 10 here. Is it clear? Uh-huh. Yes. Actually, I did not get it. I'm sorry. Uh, okay, so yeah, yeah, yes, yes. No, no, no. This is not. This is a separate case. Sorry, this is a separate case. Okay, I am confusing because like I am writing, and I am writing a lot of things in the same slide. Maybe that's why you are getting confused. Okay. Anyway, so yeah. Okay. Yeah, I'll try to, write lesser things in more slides. I mean in slides. So whenever delta S is positive, the T delta S should be higher than delta H, then only delta G will be negative. So this option is also right. So all statements are right. So these all are correct statements. So is it clear? This question, is it clear? Ah, yes. Okay. So this statement, right? Uh-huh. Yeah. One second. I think I have confused all of you. Delta S, delta H, delta G. So first, let me say that my temperature is okay. I'll just take 10 Kelvin instead of 100. So everything is 10. My delta S is also positive. Delta H is also positive. So delta G will be 10 minus 10 into 10, right? So this will be 10 minus 100. So it will be minus 90. So delta G is negative for this case. Oh, one second. Okay. So my delta S is still 10. My delta H is minus 10. And in that case, minus 10 minus 10 into 10. This will be minus 10 minus 100. In this case also, it is, no, not minus, minus 110, right? In this case also, delta G is positive, I mean negative. So in both these cases, delta G is negative. In this both cases, we can see that T delta S is greater than delta G, delta H, right? Is it clear, this part? Second case, you are not clear, this one, or the delta is negative case. Okay, so if my delta S is negative and delta H is positive, in that case it will be 10 minus 10 into minus 10, right? So 10 minus minus of 100, so this minus minus will be plus, so it will be 110, right? So in this case, the delta G is positive, so the reaction will not happen. So whenever delta S is positive, then in that case, T delta S should be greater than delta H. Whenever delta S is negative, then in that case, delta H should be greater than T delta S. So I'll show for this one. One second. Say my delta S is still 10, but my delta H is large, for example 200. So I can say, and my delta H is minus 200. In then that case, 10, no, minus 200 minus 10 into minus 10, this will be minus 200 plus 100, right? So in this case, we get minus 100. So this is, in this case, it is negative. So even if delta S is negative, we can have delta G also negative. But in that case, we need to have large delta H. That is, delta H should be much that larger than T delta S. Also, this delta H should be negative. Is it clear? I'll write properly in the next slide. So whenever delta S is positive, T delta S is greater than delta H. But when delta S is negative, and in this case, delta G is negative, and the reaction will happen. When delta S is negative, then the reaction can happen only when delta H is greater than T delta S, but this delta H is negative, that is exothermic reaction. In this case, delta G can be negative. Is it clear? The reaction will also happen. Oh. So in this question, all statements are right. We'll move on to next question. So which of the following is false regarding to a ligand diagram? So as I said, it is a plot of delta G versus temperature, so it is right. The ligand diagrams are based on thermodynamic concept. Yes, because we are talking about delta G, delta H, delta S, etc. So this is also right. Then they do not tell us anything about the kinetics of the reduction process. Actually, this is wrong because we have temperature data, and from temperature and delta G and all, we can get some kind of kinetics. So this is actually okay. So actually, even though we have some delta G, delta H, delta S, etc., as you know, from thermodynamics, we do not get the kinetics, right? So since Elegant diagram is based on thermodynamic concept, it does not give any idea about the kinetics of the reduction process. Even though we have temperature, from temperature we cannot just say, okay, this reaction will happen this much fast. That cannot be said from the Elegant diagram. So this is also right. It means that Elegant diagram do not tell anything about the kinetics of the reduction process. This one is they do not assume reactant product equilibrium. This is wrong because the Elegant diagram assumes reactant product equilibrium while for calculating the delta G, delta S, etc. So this is the wrong option. This is the answer for this question. Is it clear? Okay. This is another question from I think V2. This is a straightforward question. Which in the compound which does not contain a metal carbon bond? So metal carbon bond, which one does not have metal carbon? So this, as we know, this is a organometallic compound. So nickel is bonding with this carbon monoxide. So definitely there is a metal carbon bond here. And this one also, see, this is C2H4. This is C2H4. So platinum with C2H4. This kind of bonding is there. Draw it properly. So C is here, C is here. So this platinum carbon bond is there. So this is also not the option. Then this is, as you know, this reagent I think everyone knows, right? Magnesium and then C2H5 Br. So there is also a bond, direct bond. This one does not have because Al is connected with this oxygen, C2H5 or C2H5. So except this one, everyone else have metal carbon bond. So this is the answer. Is it clear? Okay. So this one, we make it a bit bigger. So which one of the complexes can exhibit geometrical isomerism? So from the last class we discussed about cis-trans isomerism from the which belongs to the geometrical isomerism. So as and I also discussed that this geometrical isomerism is possible for square planar and octahedral generally. For tetrahedral it is not possible because for example this one I will show zinc NH3 NH3 Cl, then Cl. This is pyramid. this okay, NH3, this actually I am showing the Cl is actually behind this NH3. It's not on the same plane, you know, right? The tetrahedral structure like CH4, this is similar to that. So CH4, as you know, this is not a planar compound. It is uh, it is a tetrahedral, that is this Cl is behind NH3, right? This Cl is also behind NH3. So there all these positions are the same. So there is no difference if I keep this NH3 here or the Cl here, because all positions are the same here. That's why this tetrahedral compound does not have any geometrical isomerism. Here we have to note that it is the, we are asking geometrical isomerism, but tetrahedral complexes have something called the optical isomerism. So if the question is about optical isomerism, definitely most of the time tetrahedral complexes will have optical isomerism. Since it is about geometrical isomerism, this one we can rule out because it is tetrahedral. Then square planar also we have cis and trans, but we need to have at least two sets of ligands. For example, I'll show for platinum. Platinum we have NH3, NH3, Cl, Cl. So this is a cis isomer, and if I um, change this by Cl, NH3, Cl. Now this is a trans isomer. So for this one it is possible because we have two isomers, cis and trans. For this one, the copper one, copper NH3, I'm just giving N for NH3. So in this case, everything is the same. There is no point if I change this NH3 to this place or this NH3 to this place. It is all are equivalent positions. So this square planar complex does not have geometrical isomerism because all ligands are the same. For square planar complex, at least you need to have two sets of ligands, like here NH3Cl. Now octahedral also, we for octahedral to get a geometrical isomerism, there should be at least three ligands. See, for example, here it is not possible because I have one chlorine here, NH3, 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 then NH3, NH3. So there is, if I keep my chlorine here also, it has equivalent positions because both are always it is surrounded by NH3. If I keep it here also, it is the same because always it is surrounded by NH3. So here also all are equivalent positions. So there is no geometrical isomerism for this octahedral complex. For octahedral complex, we need to have at least three types of ligands. Is it clear? Oh. uh, So this question is the magnetic measurements. Yeah, I did not understand. But the question is which one of the following can exhibit, right? So since it is can exhibit, there is only one option. But if the question was about which one cannot exhibit, then you can take all of these. If the question has multiple answers, you will be able to put multiple ticks. Most of the time, I think they allow multiple answers because to confuse you more, to like let you know that there sometimes it confuses us, right? Because we think that okay, maybe all are possible, which one is right, we don't know. So sometimes I think they give like multiple options, like we can submit also sometimes depending on what form they're in. So all the time, most like you have to write down and check, then give the answer, because sometimes we may overlook some of the options and we will lose the mark. Okay, so this is also a straightforward question. The magnetic measurements indicate that cobalt OH2, that is water, cobalt water complex has three unpaired electrons. Therefore, the hybridization of the metals orbitals in this complex is. So, as you know, cobalt is in 2 plus state here, right? And it has three unpaired electrons. I'll just draw the d orbital. Okay, then the outer s, then the outer p. So this is 3d for s, for p, for d. So it already cobalt 2 plus has d7 electrons, and it is saying it has unpaired electrons. So first we will fill one by one, 5, then 6, 7. So yeah, just by filling singly, then pairing up, we have like this 3 unpaired electron as in the question. So all these are remaining for the hybridization. Now we have to look at how many number of ligands are there. We have H2O 6. 6 H2Os are there. Each H2O will give 2 electrons. So it will be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the answer here is sp3d2 because 1s, 3p, 2d. Right? So for these questions, first you will have to look at for what metal they are asking and what is the oxidation state of the metal. And if they have, like in this question they have said that it has 3 unpaired electrons, so we have to arrange it in that way according to the number of electrons in in that oxidation state, and uh, whatever orbitals are remaining, they are available for hybridization. Now we have to look at how many water molecules or how many ligands are there. So since we have 6 ligands and these are neutral ligands, each ligand will give 2 electrons. So 2, 4, 6, 8, 10, 12, right? So this many is needed for hybridization for this complex. So this is the answer. Is it clear? Okay. So before moving on to this crystal field questions, I'll just give a brief overview about crystal field splitting below. Okay, so yeah, so I am first initially looking only at the octahedral compounds or the octahedral ligand field. So first the metal and the ligands are at an infinite distance, like at a distance where they can't see each other, there is no interaction. That is the stage 1. And in the stage 2, these ligands are surrounding the metal in a spherical fashion. So this is called a spherical field. So initially in the stage 1, the metal was like fine without any interaction with the ligands. So they were all having the same energy, the degenerate orbitals. All 5 d orbitals were having the same energy. And when in the stage 2, when the ligands are coming much closer, there is a spherical field. Because of that interaction with the ligands, this energy of all the d orbitals are raised equally. Still the degeneracy is kept here, but the energy generally is just increased to a higher energy. In the stage 3, the orbitals are the ligands are attaching are ligands are interacting with the metal through different axes. Some are attacking from z axis, some are from x axis, some are from y axis, and so on. So due to different orientations or alignments of the ligands with respect to the metal, then we have a splitting, because some of the orbitals, as you know, uh, okay. So some of the orbitals, for example, let me draw dxy. So dxy is something like this, right? They are in between the axis. But if you look at dx square minus y square or dz square, it is somewhat like this. This is dx square minus y square. They are along the axis. So whenever a ligand is attacking through the axis, then all the d orbitals which are present on the axis feels much more repulsion from the electrons of the ligand compared to this one, because here this orbital is in between axis. So if, okay, let me say that my ligand is coming from here, and my ligand is coming from here, and already there is a strong already there are electrons here, and when my ligand is coming from here, there is a strong repulsion between these axes which are present, which between these orbitals which are present on the axis when the ligands are coming through the axis. But when ligands are coming, in this case my ligands are still coming through the axis, but my electrons are somewhere here in the d orbital, so they don't have that much repulsion compared to this case. So that is why we have a splitting here. Dx square minus y square and dz square have a splitting. They have a higher repulsion. That's why they have more energy than this set. They are somewhere like this, between axes. They have lesser repulsion. Therefore, they have lesser energy. So that's how this set is the T2G and this is the EG set in the octahedral. And now this is stage 3, but stage 4 is the stage 4 is when the actual complexation happens. So complex forms because complexes are stable. The stability is coming from something called as CFSE, or the crystal field splitting energy, or LFSE, ligand field splitting energy. So after this happens, the metal relaxes to this kind of as lower energy. So compared to the free metal, the complex is much more stable. See, the first the metal was here. Now the T2G has got a lower energy than the original metal. So that's why metal likes form complexes, because from its free state it is getting a lower energy configuration. So now we have T2G and EG. Now if I keep one electron here, each electron will have a contribution of minus 0.4 if it is in T2G. If it is in EG, each electron will have a contribution of 0.6 delta. So this delta oct or dq, it is not a constant value. It changes depending on the nature of the ligands, the identity of the metal, the oxidation state of the metal, and the number of the ligands. So delta oct, as I said, is not constant. See here, for example, I have given different complexes, and you can see different delta, right? So this delta of depends on how much splitting is happening. So nature of the ligands, as we know from the spectrochemical series, we know each ligand split the crystal fields separately. So weak field or strong field in that case. Then the identity of the metal, if it is belonging to 3D, 4D, or 5D. So generally 4D and 5D metals split the crystal field much more strongly than 3D. So we can just say 3D, 4D, 3D is less than 4D, less than 5D, the delta oct. Because the 4D and 5D metals are much more larger than the 3D. Because of that, they have a much more repulsion to the incoming ligand. That is why when the repulsion or that interaction is more, right, that is why we have larger delta oct. Then we have the oxidation state of the metal. So whenever we have something like, okay, cobalt 2 plus and cobalt 3 plus, in this case cobalt 3 plus will have higher delta because cobalt 3 plus has a higher oxidation state. When the oxidation state increases, it means that the charge is increasing, right? The 3 from 2 plus to 3 plus, the charge is increasing. The nucleus is much more able to attract the last electron. Now the cobalt 3 plus will contract. So the size of the cobalt 3 plus will be much smaller than the cobalt 2 plus. When the metal is small, then this metal ligand uh, bond length is also small. If the bond length is small, it means that there is much more stronger interaction. So whenever the oxidation state increases, that makes the metal ligand bond small. That means the interaction is much more. Therefore, the delta oct also increases. So you have to look at the oxidation state also. Next is the number of ligands and the geometry. So the number of ligands is, if we have 4 or 6, we can the ligands can come in two ways. If it is 4, it can be tetrahedral or square planar. Then if it is 6, it can be octahedral. Generally we have other combinations also, but generally it is octahedral. So it will it be tetrahedral or square planar will depend on the nature of the metal and the oxidation state of the metal. So here, for example, the TiF6 3- and TiOH2 6 3+. Both are titanium complexes. Both have same charge. Titanium is in 3+ state, but still their delta, the crucible splitting is different. TiOH2 6 3+ has a higher delta. So can anyone say why this this one has a higher crucible splitting energy? Yes. So OH2, which is water is a much more stronger ligand than fluorine. So since it is much more stronger, the crystal splitting is also larger. That is why we have a larger energy here. So in this case, we have vanadium in 3+ state and vanadium in 2+ state. As I said, vanadium in 3+ state has much more metal ligand interaction due to which the crystal splitting increases. So is this slide clear? Okay. So to calculate CFSE or the crystal splitting energy, first you need to find out, yeah. Hmm. That is actually the common linear combinations of two orbitals. There is some other actually it is like, it is not a single orbital. It is dxy, dxz, dyz are single d orbitals, but dx square minus y square is actually a linear combination of two different orbitals. Right now I don't have the pictures to like discuss it, but it is not actually, I cannot say that it is like addition. What we call it as a linear combination, because both are similar. We can just add it up, but not the normal addition that we do. I don't know how to explain it. Maybe in another class I can, next class maybe I can show you as a separate, at the end of the next class maybe I'll show you. Which line? This line. That it is not, because it there is a minus. This comes actually from the linear combination result. Like when we combine two orbitals, we can combine it in phase or out phase. There is it is actually related to quantum chemistry. So finally we get this result, but it is not directly minusing or subtracting. Maybe I can explain it with some equations maybe in the next class. Right now I don't have it. Okay, and dz square is also similar there. It is not like directly z square is coming. It is also some combinations of other orbitals. So maybe that two together I'll show in next class. So to calculate CFSE, first we need to find the oxidation state of the metal, then find how many d electrons are there. Then based on the coordination number or the number of ligands, we have to identify the geometry. Based on geometry, we have to find which kind of splitting pattern is there for T2G, ET2G, EG or ET2. That is, for octahedral, we have T2G, EG. For tetrahedral, we have T2E. So based on the geometry, we find out what kind of splitting it is there. Then we have to find out what is it, high spin or low spin, based on the ligand, type of the metal, oxidation state of the metal. Then we'll just fill it up. Then to calculate, as you know, for each or electron will give minus 0.4. This will be plus 0.6 each electron. Yes, tetrahedral, here it will be minus 0.6. This will be plus 0.4. That's it. Same values, just the sign will be different. We'll solve some questions, then it will be much more clear. So before that, I'll just introduce the spinel. Spinel is a mixed oxide. That is, we have like something like of this state, A, B2, O4. Both where A and B are two different metals, or the same metals also, it is fine. But in different oxidation state, A will be in 2+, the B2 will be in 3+ state. In the normal spinel, we have two kinds, normal and inverse. In the normal spinal, all the A2 plus will be occupying the tetrahedral side, and the trivalent, that is the plus, the B3 plus ions will be occupying the octahedral sides. So basically this is the formula. A2 plus will be in tetrahedral, B3 plus will be in octahedral. But in inverse spinal, the plus 2 A metals are in octahedral sites. First it was in tetrahedral, now the A2 plus is in octahedral. The B, we have two B, right? So one B will occupy the tetrahedral, other B will occupy the octahedral side. So is it clear? Normal spinal will have A2 plus in tetrahedral and B3 plus, both B3 plus in octahedral. In inverse spinal, the A2 plus will be occupying the octahedral, while the one of the B3 plus will be in tetrahedral and the other 3 plus will be in octahedral. So how to find out which is normal, which is inverse? That is based on the CFSE. So this is the normal spinal's formula, and for having a normal spinal, the CFSE of B3 plus should be greater than CFSE of A2 plus. Then it will be normal spinal. The inverse spinal will be when CFSE of A2 plus is greater than CFSE of B3 plus. So essentially, whenever the CFSE is high, that metal will occupy the octahedral side. But if it is B3 plus, it will be normal spinal. If it is A2 plus, then it will be inverse spinal. Is it clear? Okay. So, a normal spinal has no any spinal has A, B, then offer. I am writing A2 plus, B3 plus, then there are 3 B plus. I mean 2B and 1A. 1A is in 2 plus state, B is in 3 plus state. So normal spinal, the A2 plus will occupy the tetrahedral side in the lattice. So here we are talking about a solid state lattice structure. Then I think you know some like FCC, BCC and so on. So this FCC lattices will have a hole, like a vacancy. So that kind of vacancy can have a different shape, tetrahedral or octahedral shape. Like octahedral in the sense that each hole is like separated, each hole is surrounded by 6 atoms. In that case it is octahedral. If it is surrounded by 4, it is tetrahedral and so on. So in normal spinal, this A2 plus will be in tetrahedral and both B3 plus will be occupying the octahedral vacancy. But in and this is when the B3 plus's CFSE is much more higher than A2 plus. So whenever the CFSE is high, then that metal will occupy the octahedral. See, B3 plus has a higher CFSE, so it will occupy the octahedral side. Now the inverse spinal, this is the same formula, but in inverse spinal case, the CFSE of A2 plus is higher than B3 plus. So as I said, whenever the CFSE is high, that will occupy the octahedral state. But if it is A2 plus, it will occupy octahedral state, but there are two B plus. There are two B3 plus, right? So one B3 plus will also occupy octahedral, octahedral state, and one tetrahedral state, right? No, you can yeah, you can say both, because it is called a stabilization energy because it stabilizes the metal when compared to the normal free metal. That's why it is called a stabilization energy. You can also call it a splitting energy because it is splitting this degenerate orbitals into 2 sets or 3 sets or how many sets, like depending on the ligands, number of ligands. And actually CFSE is an outdated model. Nowadays we have something called LFSE ligand. We have something called ligand field theory. Ligand field, just for in CFSE we are looking at each ligand as a point charge, like there is no covalent interactions. That assumptions we are taking in CFSE, the crystal field theory. And whenever we are dealing with crystal field theory, we deal with the crystal field splitting energy. The ligand field theory just says that there is some kind of covalent interactions as well, but that is the more accurate picture. So that we just call it as for whatever the splitting happening in that, it is called ligand field splitting energy. But essentially it is the same. All the things that we do, like the number of electrons, how they affect and all, are generally the same. So we sometimes we just say LFSE or CFSE like they are synonyms, right? Okay. So is it clear? Spinal conversation is clear. Spinals. Hello. Am I audible? Okay. So it is clear, right? Okay. So okay. So you did not hear this whole discussion, right? Hmm. Ha ha. Okay, that you heard, right? Okay. So but the spinals you could not hear. Okay. So just that in spinal we have this A2 plus and B3 plus. There is only one A2 plus, but B3 plus can be two. There are two B3 plus, right? So in a normal spinal case, the CFSE of B3 plus is much larger than the A2 plus. So whenever the CFSE is large, that metal ion will occupy the octahedral side. So in the normal spinal, both B3 plus will occupy the octahedral side, A2 plus will occupy the tetrahedral side. Now, yeah, if CFSE of A2 plus is larger than B3 plus, in that case, as I said, A2 plus will occupy octahedral side, but there are two B3 plus, right? So one B3 plus will occupy octahedral, the other will occupy the tetrahedral. That is the change. So essentially, we have to look at the CFSE of both B3 plus and A2 plus to understand if the spinal has a normal or inverse structure. That we will solve some examples, then it will be much more clear. Yeah. Before moving to that, I'll just talk about this spin only magnetic moment, because we'll be solving some questions with it. The spin only magnetic moment comes whenever there is no orbital interaction. So this is the actual equation, US plus UL. US is the spin only magnetic moment, UL is the orbital angular moment, orbital magnetic moment. So whenever the orbital magnetic moment is not considered, then we get this formula. But when we consider that, we have to use this formula. So when do we have to consider the orbital angular momentum? Whenever the orbitals are degenerate, like we have T2G and EG, right? So whenever we have a T2G or EG set, in that case we have to consider, like, if the electrons are present here, and the orbital should be similar in shape and size, so that they are transferable into one another by rotation about the same axis. So this is actually I have shown in the picture. If we look at the dxy, dxz and dyz, if I rotate each by 90 degree, we can we can transfer actually both. Like if I rotate dyz into by 90 degree, I essentially get the dxy. If I rotate dxy 90 degree, I essentially get the dxz. So we can, by rotation, we can interconvert these axes. So whenever the electrons are present in these axes, this electron can move to this orbital, or it can move to this orbital, and so on. So since this movement is there, that orbitals contribute. There is a orbital spin coupling will happen. Normally, the magnetic moment comes from the unpaired electron, that is the spin only moment. But whenever the electron can jump from one orbital to the other, that orbital coupling will also happen. Then in that case, we have to consider the orbital angular momentum as well. So another important thing to note is that electrons in T2G orbitals can contribute, but EG cannot, because EG is dz square and dz square, x square minus y square. They cannot interconvert into each other. Just by rotation, it is not possible to interconvert. So whenever the electrons are present in EG, in that case we will not look at the orbital angular momentum, but whenever it is present in T2G, we will look at. For example, in this case, I have two unpaired electrons, right? But it is in T2G. So in this case, I have to look at the orbital angular momentum because this electron can go here, this can go here, and so on. But if I have a case where one electron is here, this is the EG set, this electron cannot go here because these orbitals are not interconvertible. So in this case, we don't have orbital angular momentum. Here we have. Is this clear? Degenerate means having the same energy. Like here we have three orbitals, right? dxy, dxz, dyz, they all have the same energy. That is what degenerate means. The same. No, like whenever, 1 second, I'll just explain. For example, I have say a d4 contribution, d4 electrons, and I am in an octahedral field. So, and if I am having a weak field ligand, then I have something like this, right? This kind of electronic configuration. So here I have to look at first I look at how many number of unpaired electrons are there. Here all are unpaired electrons, so there are four unpaired electrons are there. But here will orbital angular momentum matter? Because here already the orbitals are filled, like at least one electron are there. So now it cannot go here and there. But whenever the here it is there, okay, I don't know. Let me take another example. Let's say it is. Just take another example. Let's say it is a D7 configuration and the number of electron is just unpaired electron is 1. So whenever we are looking at the magnetic moment, we look at the unpaired electrons and where this unpaired electron is present. So here the one unpaired electron is present in the EG orbital. So now this electron cannot go here because these orbitals are not interconvertible into each other. So in this case, mu L is not there. We can just use the mu S formula. Mu S formula was root of n into n plus 2. So just by that, we can calculate the orbital angular moment, the magnetic moment, root of n into n plus 2, which is equal to n here is 1, so 1 into 1 plus 2, so root of 3. Magnet. This is the unit. Bohr magnetron. So in this case, we don't have to look at the mu L. But if the case was something like this, D2 configuration, EG and T2G, here the number of unpaired electron is 2. Here I have to look at both mu S and mu L because here one like vacant orbital is there, this electron can come here, this electron can come here, because these orbitals are interconvertible if we just rotate by 90 degree. So in this case, we have to use the larger formula, which is mu S plus mu L. That is the mu effective, which is equal to root of 4s into s plus 1 plus L into L plus 1, this formula. But if the question is specifically asking for spin-only magnetic moment, then you can use this formula. Otherwise, if it's just asking what is the magnetic moment of this complex, then you have to write down the configuration and check if there is any orbital contribution. If there is any orbital contribution, you have to use the bigger formula of mu S plus mu L, which is equal to root of 4s into s plus 1 plus L into L plus 1. Is it clear? Condition Um, Condition for degeneracy. Ah, no, here they what they are saying is, if I have some, like if I have an electron in the T2G and if I have an electron in EG, I can't compare this T2G and EG because T2G is having a lower energy and EG is having a higher energy. These are not degenerate, right? So the interaction is possible only if we are in a degenerate set of orbitals. I can only look at the electron in the T2G. Like if I am looking at an electron in the T2G, I have to look only with T2G. I cannot say that okay, my electron can go to EG or something like that because EG is not a degenerate orbital with respect to T2G. So we can have contributions from these three degenerate orbitals in T2G or these two degenerate orbitals in EG. Is it clear? Oh, then third one is orbitals must not contain electrons of identical spin. In this case, it is the orbital angular momentum contribution will not be there because at least one vacant space should be there where this electron can jump. Here, already all orbitals have the same like the same spin electrons. So there are in that case it cannot jump. But in we can have in a separate case. Uh, Example. In this case, these downspin electrons can come here because here we do not have a downspin space, a downspin electron, that vacancy is there. In that case, this downspin electrons can come here. In that case also, orbital angular momentum will be there. Is this point clear? Okay. So then we will solve. Yeah. Huh. Can you tell once again? Hmm. Okay. Yes, yes. This case, right? Uh, but you are talking about 6 electrons. No, in 6 electrons, then there is no vacancy, right? Because each orbital has both up and down. Now there is no vacancy for because the criteria is orbitals must not contain electrons of identical spin. So if a up spin electron have to jump to somewhere, it should not have this up spin. Here this up spin cannot come here because already then up spin is here. When all 6 electrons are filled, the even this downspin has a like a another downspin electron is there, right? So this cannot come here because the same spin is there. 4 electrons, like 1 second. 4 electrons where T2G, like this. Yes, in this case, this downspin can come here and here. Here newel will be there, but in this case, it won't be there. Now we will solve some questions. Huh. The crystal field splitting energy for COCl6 4 minus is 18,000 centimeter inverse. Delta for COCl4 2 minus will be. So here we have delta which is 18,000 centimeter inverse. This is for COCl6 4 minus. So can you please write in the chat box what is the oxidation state of cobalt here? What is the oxidation state of cobalt? Yes, cobalt is in 2 plus state, right? So everyone is clear, right? How we are saying that cobalt is in 2 plus state. Okay. So since cobalt is in 2 plus state, it has d7 electrons, and we are looking at the octahedral complex. So T2G Eg, and it is a Cl is a weak field ligand. So first we will singly occupy, then we will pair. So 1, 2, 3, 4, 5, 6, 7. Is this clear? Okay. So for this one we will calculate the CFSE. So each T2G electron will have minus 0.4, minus 0.4 into how many electrons do we have? 2 plus 4 plus we have 5 electrons, right? Plus 0.6 into 2. So this will be minus 2 plus this will be 1.2. So we have minus 0.8 delta O. This delta O is the important thing to note here. This delta O is not fixed here. It is a variable depending on each complex and the oxidation state and the metals properties, etc. So we have that minus CFSC delta is equal to minus 0.8 delta O. And delta we already know 18,000 something. So 18,000 is equal to minus 0.8 into delta O. So delta O we can calculate here. Delta O will be 18,000 divided by 0.8. So how much will be delta O? And let me calculate. Ah, that is also possible. Yes, I forgot about that. Yes. Yes, that will be much more easy. Delta octahedral is equal to 4 by 9 of delta tetrahedral is equal to delta 4 by 9 of delta O, right? Okay. Actually, you're right. Uh, since it is an tetrahedral complex, we can directly do like this. But otherwise, from this, since both cobalt is in plus 2 state, both cobalt will be having the, and both ligand is also the same. So in that case, this delta O will be a constant. As I said, delta O depends on the ligand, the metals, oxidation state, and the identity of the metal. In both cases, cobalt is in 2 plus state, Cl and the ligand is also the same, but the splitting is different. So from that we can calculate. Okay, splitting is different. I forgot that. Okay, thank you for letting me. Since if both the complex were in the same having the same coordination number, from that we could calculate the delta O. Then we can just substitute and find out. In this case, this is an octahedral complex. This is a tetrahedral complex. So we already have a relation delta T is equal to 4 by 9 of delta O. So we'll just write 4 by 9 of 18,000 something. How much is it coming? Yes, yes. This formula can be used whenever there is a tetrahedral and octahedral complex are there. This is a general relationship. Yes, yes. And also, like actually, I think I confused you because delta O should be the same here, which means that the metal and the ligand should be the same. In that case, we can split for the same ligand and for the same metal. Then we can use delta T is equal to 4 by 9 into delta O for this tetrahedral complex crystal free splitting energy. So it is coming around, I think, 8,000. Yeah. So the answer is 8,000. Okay. This is a spinal related question. The number of manganese ions in tetrahedral and octahedral sites respectively in Mn3O4. So Mn3O4 will be Mn2 plus and Mn3 plus, Mn3 plus O4. This is what they are meaning by this. This is since they are asking about tetrahedral and octahedral site, you have to know that they are talking about spinel, and spinel generally has A2, A2 plus B3 plus structure, but there will be 2B. Since all are Mn here, then one Mn will be in 2 plus, other 2 Mn will be in 3 plus 2. Now we will calculate the CFSE for Mn2 plus and CFSE for Mn3 plus. Can you please solve what will be the CFSE for Mn2 plus in the chat box? CFSE for Mn2 plus. So maybe I'll give you a hint. Mn2 plus has d5 electrons. And another hint is that this is a tetrahedral complex since O4. Okay. Okay. Maybe we can discuss now. Okay. Okay. As you said, Mn2 plus CFSE of Mn2 plus is 0, because I'll just discuss how. Mn2 plus, as I said, is T5, and oxygen we are considering as a weak field ligand, so there is no pairing up. So 1, 2, 3, 4, 5. So minus 0.6 into 2 plus 0.4 into 3. So this will be 1 minus 1, 1.2 and 1.2, it will be 0. So for Mn2 plus it is 0. So what about Mn3 plus? One person has solved. I'll give maybe 1 or 2 minutes for others to solve. Mn3 plus. What will be the CFSE for Mn3 plus? Okay. Okay, so Mn3 plus will have d4 electrons, right? This 2 plus is d5. For getting one more plus, we have to remove one more electron. So it will be d4. 1, 2, 3, 4. So CFS will be minus 0.6 into 2 plus 0.4 into 2. It will be minus 1.2 plus 0.8. So minus 0.4 delta O, delta T, not delta O, delta T. Is it clear? I okay. So so you have to be careful about the number of d electrons. If you know the number of d electrons, you can solve the question easily. So basically, we have the CFSE of Mn3 plus is minus 0.4 delta T. So Mn3 plus CFSE is greater than Mn2 plus. So this will be a normal spinel. No, negative sign just means that actually it should be negative, because negative sign means that your complex is stable. See, here we have the T2G. I mean, here, for example, here we are dealing with EG and T2G. Here we are taking minus 0.6 per each, because this is the 0. With respect to 0, it is much more stable. That's why we are taking minus 0.6, and here it is not stable. That's why we are taking plus 0.4. Is it clear? And in octahedral case, it will be opposite, minus 0.4 and plus 0.6. So here Mn3 plus has a higher CFSE than Mn2 plus. So as I said, for the normal spinels, we have this the metal 3 plus, which have a higher CFSE. So Mn3, both Mn3 plus will occupy octahedral site. The Mn2 plus will occupy tetrahedral site. Right, so the question is manganese ions in tetrahedral. First they have asked about tetrahedral and then octahedral. So this option A. Is it clear? Okay. This is also an interesting question. The magnetic moment of the complex K3COF6 is 5 Bohr magnetron. The total CFSE will be. So here we have the magnetic moment. From the magnetic moment, we have to calculate the number of unpaired electrons. Then we have to calculate the CFSE. Right? So generally, when we give okay, so here we'll have to look at, first we'll look at the the oxidation state of cobalt. Can you please put it in the chat box? What is the oxidation state of cobalt? Yeah, right. So the oxidation state of cobalt here is 3 plus. So cobalt in plus 2 state has D7. Cobalt in plus 3 state will have one more electron removed, so it will be D6. Right? This is clear, right? Cobalt 3 plus will have D6. Now, we also know that F is like a weak field ligand, but first we'll try, and also this is an octahedral complex. First we'll try like a weak field ligand, 3, 4, 5, 6. So 4 unpaired electron, right? Another case is also possible. 1, 2, 3, 4, 5, 6. Since sometimes the metal, if it is in a higher oxidation state, even if we have a weak field ligand, this kind of pairing can happen. But in this case, clearly they have mentioned the magnetic moment is 5. If there is no unpaired electron, then there is no magnetic moment. So for cobalt 3 plus, if it is a high low spin complex, there is no unpaired electron. So this is definitely not the configuration. This is the configuration. So this one I have to draw properly. 1, 2, 3, 4, 5, 6. Okay. So now we can calculate the total CFSE. Can you calculate total CFSE? This is the T2G level. This is the EG. Each T2G will be, each electron in T2G is will be giving minus 0.4. This will be plus 0.6. Can you put it in the chat box? What is the answer? Okay. I'll give you, yeah, yeah, right. So I think now you have understood. So CFSE will be minus 0.4 into 4 because there are 4 electrons in T2G plus 0.6 into 2. So 1.6 plus minus 1.6 plus 1.2, this is minus 0.4 delta O. So option A. Is it clear? This is a straightforward question. The structure of MnCl4 2 minus is. So from the just from the complex, we will know that we have 4 Cl. So it can be tetrahedral or it can be square planar. Since this is Mn is a 3D metal. For 3D metal, yeah, this one, yes. Do you want me to explain once again? Oh, okay. This calculating the CFSE step. Okay. So this one you understood, right? How we have wrote the how many electrons are there in T2G and how many are in EG. Okay, okay. So CFSE is equal to minus zero point 0.4 into 4 because there are 4 electrons in T2G plus 0.6 into 2. 2 are coming from EG. So this is minus 1.6. 0.4 into 4 will be 1.6 and it is minus plus 0.6 into 2 will be 1.2 which is equal to minus 0.4 into delta O. Right? Okay. So this one, as we were saying, we can have, if we have 4 ligands, we can have tetrahedral or square planar structure. And since manganese is a 3D element, 3D element generally will have tetrahedral complex for coordination number 4, except for the case of nickel. Nickel can have tetrahedral and square planar depending on the nature of the ligands. Since this is a manganese, definitely this will be tetrahedral. So is it clear? Yeah. This one is also a straightforward question. Like you just need to put in into the equations and then you'll find out. So do you need me to solve this or can we move on? Let me check the chat box. Maybe we'll solve it at the end because this is not related to the CFSE or the spinals that we are dealing right now. Um, Yeah, this one will solve. This is also a general question. Carbon monoxide is isoelectronic group. So carbon, we normally we can deal with the if it's a larger metal or atom, we can normally deal with the we can take the valence electron. Since this is carbon and oxygen are like small, we can take the total number of electrons. So carbon total number of electron, the atomic number is 6, oxygen is 8. So for carbon monoxide, 6 plus 8, 14 electrons are there. So can you find out from the option which will have the same number of electrons as of carbon monoxide? Okay, maybe we will discuss. There is no need for discussing the last question. Maybe not. We don't discuss. We won't discuss. Yeah. So I'll give you one more minute to find out. Okay, good. So we'll just solve this. So O2, this is O, 2 minus. So oxygen, as I said, has 8. So 2 minus means we'll add 2 more electrons. So it is only 10 electrons. So definitely this is not the answer. Then this is nitrogen. Nitrogen has 7 electrons. So 7, but it has 2 plus, which means that we have removed 2 electrons. So it is 5. So definitely this is also not the case. Then Cn minus, C 6, then N, as I said, 7. Then we can, there is one negative, so we have to add 1 electron. So 7 plus 7, 14. So definitely Cn is the right answer. We'll anyways check for O2, O2 plus. So as I said, oxygen has 8. Then we have to remove 2 electrons because it is 2 plus. Then it is 6. So Cn minus is the right answer. Is this clear? Okay. Now, this is something called the yawn-teller distortion. So before that, I'll just show. I'll discuss it here. First, let me write the splitting pattern for octahedron. So we have the XY, the XZ, the YZ. This is the T2G level. Then we have EG level. This is the X square minus Y square, the Z square. Right? This is for octahedron. Now, whenever the this is a very symmetric structure. Like octahedral is a very symmetric uh, configuration, but the scientist called Jon Teller told that like it is not possible to have a highly symmetric structure and degeneracy together unless it is a linear molecule. For example, if it was like something like this is a linear molecule. In this case also it is highly symmetrical because in both side we have Cl. In this case we can have maybe degenerate orbitals and symmetry together, but in cases like octahedral complexes, where this is definitely not linear. Linear means just straight. This is a octahedral complex. It is not straight. These four are in the plane, these two are above and below. Definitely this is not a plane, it's not a linear molecule. In this case it cannot have this symmetry and degeneracy together. Since it is already symmetrical, we can't do anything about the symmetry, but it can change the degeneracy. The degeneracy lifting will happen. So as we know, octahedral is like this, but not always. Sometimes what happens is, because of this highly symmetric nature, this degeneracy can also split. That is, this EG can split into two levels, T2G can split into two levels, and so on. That will happen when um, for some, there are some prerequisites that there should be, the electron should be present in EG orbital, then only this will happen most of the time. And there are two types, Z out and Z in. It is also called tetragonal elongation or tetragonal uh, compression. Z out means whatever orbitals having this Z component will be now feeling lesser repulsion, because now the okay, I'll just show like this. I have metal, then so all these are in plane. This all A's are in plane. This is for octahedral complex. So this is in a XY plane, and this B is in a z axis, because it is, this is a plane and B are above and below the plane. So this is in the Z axis, this is in the XY plane. So in this case, this B can come closer to the metal or it can go far from the metal. When it goes far from the metal, that is called Z out. In that case, all this A will come closer. So what happens is, since Z is going much more far away from metal, it has lesser interaction with the metal. Therefore, the repulsion is much less. Therefore, the energy of the Z square orbital will decrease. It will decrease to, I'll show it in a new slide. Dxz, dyz, dxy. So wherever the z contribution was there, that energy is now getting lowered because the interaction between z orbital and the ligand is much lesser now. So there is, since if it is lesser interaction, it means lesser repulsion, therefore lesser energy. So this dz square orbital will now decrease its energy. It will become much more stable now. So it is like this now. And here also this degeneracy will shift because this dxz, dyz components will also come down. So this is dxy, but these two orbitals are now stabilized, much more stabilized. This is in z out. So when Z in happens, the other way around. Z in will, when Z in happens, there is much more interaction between the Z orbitals and the ligand. Therefore, Z's repulsion will be much more higher. So with respect to this, dz square will be having higher energy. Dx square minus y square will have lower energy, which is it is much more stabilized with respect to z square. Here it will be dxz, dyz, here it will be dxy. So this is z in. So for Ion-Teller distortion, we can have either of these cases, z in or z out. So from just by looking at the molecule, we cannot say which is z in, which is z out. But that is not important. We just have to find out if it has Ion-Teller distortion or not. So generally, it is seen in like copper complexes where D9 systems. So first, the metal was in a kind of degenerate state. We had T2G, EG, but because of Ion-Teller distortion, that is, the degeneracy is now shifting. Degenerate orbitals are splitting into splitting into more number of orbitals. This T2G split into two types, and EG also split into two types. This can happen two ways: Z out and Z in. Is this clear? Hello. Okay. So now we will try to solve which one has Ion-Teller distortion. So first we will find out what is the number of d electrons, and all are as you see in uh, octahedral environment. So first one, cobalt is in 3+ state. So cobalt 2+ has d7. So cobalt 3+ will have d6 electrons, and octahedral. And NH3 is a weak field ligand. 1, 2, 3, 4, 5, 6. Okay, so Ion-Teller distortion has two types: dynamic and static Ion-Teller distortion. So this EG level has much more stronger Ion-Teller distortion. So whenever electrons are present in EG orbital, then we will have strong Ion-Teller distortion. But here also it should not be equally occupied. There should be at least one unoccupied level. So now we'll solve for chromium. Chromium is also in 3+. So scanning titanium, vanadium, chromium. Chromium in +2 state has D4. So in +3 it has D3. So it is just 1, 2, 3. Here also Ion-Teller distortion is possible in T2G, but it is much more weaker. But there should be at least one vacant state. since it is all occupied, here also we cannot have joint layer distortion. Here also we don't have joint layer distortion. Now you look at copper 2 plus. Copper 2 plus has d9 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9. Here this up downfield electron can go here, right? So because of this, here we have strong joint layer distortion. Strong because it is this unpaired electron. This electron is in the EG. Whenever this kind of interaction is happening in EG, that is strong. Whenever it is happening T2G, it is weak. For Fe, for Fe, here Fe is in 2 plus state and D6 electron, and Cn is a strong field ligand, so pairing will happen. In this case also no non-talar distortion because there is no vacant space for the electron to be. Is this clear? Okay. This one, according to our discussion, we will solve. Which complex? The complex? Yeah. No, no. NH3 is a weak field ligand. So complex that shows orbital contribution to the magnetic moment is. So first we have to calculate the oxidation state, then we have to find out the number of d electrons, and then we have to arrange the d electrons in the T2G or EG orbitals. Then we will see which one will follow. So we will solve one by one. So here the copper, as we just solved, is copper is in +2 state, and in +2 state copper has D9 and water is a weak field ligand, and we are dealing with octahedral complexes. So T2GEG 3, 4, 5, 6, 7, 8, 9. So here, will this have an orbital contribution or not? Can you put in the chat box? Okay, so you're saying that it has orbital contribution. I am asking about, I'm not asking about the Yontaler distortion, I am asking about the orbital contribution to the magnetic moment. Yeah, so actually we don't have orbital contribution here because to the magnetic moment. Here the keyword is magnetic moment and the orbital contribution. So as I said, the orbital contribution happens when the we can just interrotate or interconvert with the axis, with the orbitals. In EG, it is not possible because dx square minus y square and dz square are two different orbitals. Just by rotation, we cannot interconvert with each other. Therefore, since the unpaired electron is here, there is no orbital contribution. So this is not the answer. Now, nickel 2 plus. Nickel 2 plus has d8 electrons. So T2G again. 3, 4, 5, 6, 7, 8. So in this case, will it have orbital contribution? Right. So in this case also, we don't have orbital contribution because see the unpaired electron is still in EG, so we don't have. Now cobalt 2 plus. Cobalt 2 plus has these 7 electrons. So 1, 2, 3, 4, 5, 6, 7. Right? So will this complex have orbital contribution to the magnetic moment? Okay. Anyone else wants to answer? Will cobalt 2 plus complex have orbital contribution? Okay. So this one has, because as you see here, there is one vacant space and this downspin electron can come here. Therefore, the orbital contribution is present. So this can be a right answer. We look at this one also, chromium 2 plus. Chromium 2 plus is D4. So 1, 2, 3, 4. As here also, the unpaired electron is in Eg, so it is not possible. Here unpaired electrons are there, but all are of the same spin. Therefore, here also there is no dual contribution. So this is also not there. So only option C is the right answer. Is this question clear? Oh, so this one you should solve. What is the spin-only magnetic moment of vanadium 2 plus? So one clue I'll give, vanadium 2 plus is in, can you get it, vanadium D3. Can it be, vanadium 2 plus has D3 electron. So what is the spin-only magnetic moment of V2 plus ion? This one you don't have to split the orbitals because there are no ligands. You just have to write the normal d orbitals, the degenerate d orbitals, and from that you just need to calculate. The keyword here is spin-only magnetic moment, and the spin-only magnetic moments, the equation was root of n into n plus 2. Can you put it in the chat box? Yeah, right, you guys are right. It is 3.87 because we have to, this is a normal d orbital degenerate, and there are 3 electrons, 3. So we just have to calculate directly. Number of unpaired electron is 3, so 3 into 3 plus 2, so it's equal to root of 3 into 5, just root 15, which will come around 3.87 Bohr magnitude. Option C. Is this clear? Okay. This is also an important question. The concept of P. P is something called as pairing energy. So whenever an electron pairs, for this pairing we need to provide some energy, that is called the pairing energy. Why do we need to provide energy? Because both electrons are of the same nature, right? Each electron has a negative charge, so negative and negative will repel, because to avoid, to overcome this repulsion, we need to give some energy to pair this electron. That is called the pairing energy, or the P. So now the question is, crystal field stabilization energy for high spin D for octahedral complex in units of delta O is. So the keyword here is high spin, D4 and octahedral. So we'll try to solve this. And it is octahedral, so we'll just first write the T2G and EG levels, and it is also said D spin, I mean high spin, and we have 4 electrons, so there is no pairing. 1, 2, 3, 4. This is high spin. Now, one second. So first we will calculate what is the crystal field splitting energy for this configuration. What is the CFSE for this? This is T2G EG. Can you put it in the chat box? Okay. Okay. So the CFSE here is minus 0.4 into 3 plus 0.6 into 1. So minus 1.2 plus 0.6. So it is minus 0.6 delta O. Is this clear? And there is no pairing, so we don't have to add the pairing energy. Yes, yes. So for that, let me take. Consider this normal d orbital where we have d6, just one set of paired orbitals there. So now if I say that I have a high spin orbital, high spin octahedral complex of d6, then I will write like this. So for this, the CFSC will be the maximum minus 0.4. This is for low spin. This is low spin. So here the CFSC will be minus 0.4 into 6, which is minus 2.4 delta O. But here there is two more pairs of there are two more pair of electrons. In the initial metal we only had one pair. Here we have two more pairs. So essentially we should write CFSC is equal to minus 2.4 O delta O plus 2P, because we have extra two pairing energy here. So if I'm taking low spin, see the question here was for high spin, what is the case? Since you asked me for an example, I just took a D6 configuration in the metal's normal state, and my question is for low spin, what is the case? If it's for high spin, 4, 5, 6. In this case, there is no extra pairing energy because it is the same as of the original metal state. So CFSC will be this minus 0.4 into 4 plus 0.6 into 2. Minus 0.4 into 4 plus 0.6 into 2 will be. No, this is not related to VBT. This is related to the normal uh, D of orbital of a metal. VBT, when valence bond theory comes into picture, we look at the other orbital like 4s, 4p, 4d, or other like 3s, something like 3s, something like that. Now I am concerned only about the 3d orbital of the metal, only this one, in its normal metallic state. So let's say for me, cobalt, not cobalt, let me say I am dealing with Fe2 plus ion. I am just dealing with the Fe2 plus ion, not with any ligands. I only have an Fe2 plus ion, no ligands are there. So in this case, still the orbitals are degenerate, right? There is no splitting. So in this case, one pairing energy is there. So if I form an Fe2 plus, if I form a complex FeH2O6 2 plus, this is a high spin complex because water is a weak field ligand. So in this case, I have something like this. So if I compare with the original D6 of the metal, then there is no extra pairing coming, right? The only CFSC will be only from the splitting. So minus 0.4 into 4 plus 0.6 into 2. So minus 1.6 plus 1.2, it will be minus 0.4 delta O. But if I was talking about FeCN6 to form FeCN6 for minus. in this case Fe2 plus is will be in high low spin because it is coordinating with a strong field ligand like Cn. So in this case CFSE will be as we calculated minus 2.4 plus extra pairing energy will be there because this pairs was not there in the actual metal. Yes, yes. Wherever the pairing is coming, that time we will write this P. But first we have to write its native configuration. That is when the metal ion was alone without any ligands. What was the configuration? With respect to that, how many additional pairing is coming? That we have to write. Yeah. For example, I'll show you one more example. For copper 2 plus D9, 2, 4, 5. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So for this D9 case, both low spin and high spin are same, right? For example, if I say I am having a high spin complex of cobalt copper with water. So 1, 2, 3, 4, 5, 6, 7, 8, 9. This is with weak field ligand. Now if I have a strong field ligand with copper, and then I'll pair my electrons first. 4, 6, 7, 8, 9. This is the same, right? So here for D9 there is nothing called low spin or high spin. So in both cases, if we look here, here also how many pairs were there? 4 pairs were there. Here also 4 pairs were there. So basically here we'll just write CFSE. What is the CFSE? There is no pairing energy because with respect to the original D9 configuration, 4 pairs was there. In the complex form also 4 pairs is there. So there is no additional pairing energy. Yeah. And another concept that you should be knowing is when does this pairing happens, like when will I have a low spin or high spin? This, as I like last class we discussed about the molecular orbital diagram, but here the pairing energy also plays a role. So whenever this delta oct is greater than pairing energy, it means that it is much more easy to pair. Yeah. Hmm. Ah, I was talking about weak field ligand. If I have a weak field ligand, for example, copper H2O6 2 plus, in this complex also I have the same picture, right? And if in this here maybe a strong field ligand like copper with Cn something, I don't know the. In that case also, yeah, strong and weak. I am here is talking about the ligands. Whenever I have a weak field or strong field ligand, I'll either pair up or I'll just fill it first. But here in the case of copper, at the end, both configurations are the same. Both are, we cannot say low spin and high spin, both are the same. Yeah. So here, as I was saying, if delta oct is the crystal field splitting energy for octahedral complexes, if this is greater than pairing energy, what does it mean? It means that it is much more easier to pair than to go to the EG, right? So if this is delta out, right? So whenever this is so high, the electron can't go there, right? So it generally will just pair up, right? If this is too high, then it is electron will be more easier for electrons, it will be more easier to pair up than going here, right? So first it will pair up, then it will go here. So that's how we get the low spin, or how what we say the strong field ligand. For strong field ligand, normally the delta of will be very large, as we discussed in last class, because the strong field ligand interacts with the metal so much, there will be so much interaction. Because of that, the splitting will be so high. So delta F is also high. So delta F is much more greater than pairing energy. That is why pairing happens. And in the other case is pairing greater than delta. So in this case, to pair, it takes so much energy. It is much more easier to go and sit here and like singly occupied. This is the case for weak field ligand, or sometimes we say high spin complexes, where it is singly filled is fine, but when the next electron comes, the pairing energy is much more higher than delta O, because this is very less. It's much more easier for the electron to go here than to come with this, compete with this, because of the repulsion and all. So is this clear? Okay. Okay. Um, which one of the this is also a crystal field splitting energy. I think by now everyone is like okay with how to find out the crystal field splitting energy, right? Okay, so this is also the same. So I think we'll solve a separate one. Ah, the correct set of electronic configurations for metal ions in octahedral coordination geometry for strong ion-Teller distortion. So here the keyword is strong ion-Teller distortion and octahedral. So out of the option, which set? There are three sets, right? Three sets. Which out of the options, which set of electronic configuration will show strong ion-Teller distortion? Can you put it in the chat box? Which is the option? Okay. No. Half filled and fully filled will not take part in ion-Teller distortion. At least one vacancy should be there. So as I said, option A is the right answer, because see, T2G6 EG1. So here, and we are looking at strong, right? So strong means it should be in EG. So here it can go. So this is right. This part is right. Then T2G3 EG1. Here also it can go. It will be strong ion-Teller distortion. So that this is also right. Then T2G6 EG3. In that case, it will be like this. Still, this electron can come here. So there will still be ion-Teller distortion. Is this clear? Weak will be if it is only in T2G, like this, the T2G1, this configuration. Here, ion-Teller distortion will be there, but this is weak. No, similar to EG also, it can be like this, or it can be like this. Here also, ion-Teller distortion is possible, but if it is in TG, it will be weak. If it is in EG, it will be strong. That is the only difference. And in half-filled and fully filled state, there is no ion-Teller distortion. So for example, here T2G, 3, EG2, both T2G and EG are half filled, so there is no ion-Teller distortion. Here also T2G is fully filled, EG is half filled, so there is no ion-Teller distortion. Here it is possible, but others are not possible, so this option can't be right. So T2G3, same, it is also half filled, so it is not possible. T2G3 EG1 is possible, but since this is not possible, this option is also wrong. And T2G1 is it is possible, but it is weak ion-Teller distortion, so this is also not right. So option 1 is the right answer. I hope it is clear to everyone. Okay. So this is also another question for spinal. So do you want me to solve this, or are you comfortable with this? Huh? Yeah, because See here, you don't have to actually solve the CFSE and all. So because we have to first we'll look at the nature of the metal, right? Because this is magnesium, aluminum. These are not 3D elements. Zinc is 3D and Fe is also 3D. But for example, first option, both magnesium and aluminum are not 3D elements. So there is no CFSE, right? There is no crystal field stabilization energy because it does not have any crystal field stabilization. Therefore, this is a normal structure only. If it does not have any crystal field stabilization, this is a normal spinel. If they are given just spinel, it means normal. If they are talking about inverse spinel, they will specifically mention inverse. For zinc, aluminum also, it is the same case because zinc in 2 plus state has D10. D10 configuration will have 0 CFSE, right? In tetrahedral or octahedral also, 3, 4, 5, 6, 7, 8, 9, 10, right? Minus 0.6 into 4 plus 0.4 into 6. Same, right? This is 0. So zinc 2 plus has 0 CFSE, and aluminum, as I said, is not a metal, like 3D metal. It does not have any CFSE. So this is also a normal spine structure. We'll take the normal thing. And here also the same case, Fe2 plus has D6 electron, and definitely magnesium is not a 3D element. It does not have any CFSE. Therefore, CFSE of Fe2 plus is greater than magnesium. This is what we expect for the normal spinal structure. So the answer is all of this. I hope it is clear. This one we solved, right? Okay. So I think we can wrap up for today. In next class, we will discuss. I do not understand the question. Can you repeat once? Yeah, some configurations has 0 CFC. For example, um, manganese 2 plus in high spin octahedral. So this is D5, 1, 2, 3, 4, 5. So minus 0.4 into 3 plus 0.6 into 2. This is 0. CFSE. CFSE is 0 here. This is one, like whenever it is a D5 configuration and high spin octahedral, it will be CFS will be 0, like for in the case of Mn2 plus. And it can be same for Fe3 plus also. Fe3 plus is also D5, and if it is high spin, then we can have the same thing. So you have to look at the nature of the metal, what metal it is, and then what is the oxidation state, calculate the number of d electrons, then you have to put and find out what is the CFSE. Normally, see, it is spinal structure, as we know, is A2 plus and B3 plus, right? So if we write something in the front, generally we assume that it is 2 plus, this is in 3 plus. So this case also it is 2 plus, this is 3 plus. Since the question is about spinals. No, still we will write the same thing. Otherwise, you can just calculate here, because magnesium, as you know, is a s orbital. I mean s block element. It normally has the charge of +2 whenever it is in a complex, right? Because it has like 2s2, like ns2 some configuration, it generally loses this 2 electron to become +2. So in this case we can just just calculate, because oxygen He'll have 2 minus, so 4 into 2 minus plus 2 plus, from that we'll calculate T3 plus. That is also possible. Yes, yes. Hmm. If in question number 5, okay, actually the questions are not arranged properly. This one. Ah, ha, ha. Okay, let me take this one. Structure of, not this one. Check this one. This one. Which of the following complexes can exhibit geometrical isomerism? I think it is this one, octahedral. This one, yeah, this one. You need to. Okay, I'll explain. Yeah, so first we'll look at the number of ligands, right? So we have only 4 ligands. So there are 2 options, tetrahedral and square planar. And now we'll look at the nature of the metal. It is 3D. So 3D metals generally have only tetrahedral complexes except for the case of nickel. Nickel can have tetrahedral and square planar complexes. And if it is like a nickel is with CN4, then it is square planar. But if nickel is Cl4, it will be tetrahedral because this is a strong field ligand. Therefore, it prefers square planar because square planar has much more. It is much more like the CFSE is much more high. So in that case, nickel CN4 will be square planar. But since this is manganese, it's a normal 3D element. It will be tetrahedral. So I think we'll wrap up. If you have any other doubts, we will discuss that. Otherwise, we will wrap up. If you have any doubts, you can put it in the chat box also. Okay, I hope you don't have any other doubts. Then we will see for the last session. Yeah, you have any doubts? Okay. This one, magnetic moment of V2 plus ion. This one, magnetic moment of the complex K3COF6. Okay, I'll explain. So, the complex is K3COF6. So do you know how to identify, how to calculate the oxidation state? Yes. So cobalt is in 3 plus state, right? So cobalt in 3 plus state has D6 electrons, right? Also we know that F is a weak field ligand, and even if you don't know that, they have given that the magnetic moment is 5, which means that there is at least one unpaired electron, right? Otherwise magnetic moment will be 0. So cobalt 3 plus in D6 state can have two configuration, this low spin state or the high spin state. The low spin state is not possible because there is some magnetic moment. Definitely this is not the configuration. So it should be this configuration, and we have D6. So first we will singly occupy, then we will doubly occupy. Pairing is also there. Now the CFSE will be for each electron in T2G, it will we will the contribution is minus zero point 0.4. So there are 4 electrons, so minus 0.4 into 4 plus each electron Eg will have 0.6 contribution, so 0.6 into 2. So this is coming around 1.6, this is 1.2. So minus 1.6 plus 1.2 is minus 0.4 delta O. So the option A is the right answer. Yeah. Any more doubts? Okay. So for organometallic compounds, we will consider the metal in its normal oxidation state, zero oxidation state. So vanadium, this is not vanadium, tungsten. Tungsten in its plus 2 state has p4 electron. So tungsten in zero state will have d6 electron. So we already know 6 plus. Then for there are two Cp we don't know. So we'll just keep it as X and Y plus each carbon monoxide will have 2. So we have 2 to 2 4, which gives 18. So X plus Y plus 10 is equal to 18 and X plus Y is equal to 8, right? 18 minus 10. No, I do not understand. That time in carbon monoxide, I counted the total number of electrons. Here I am just counting the contribution of each carbon monoxide in the organometallics. But here I can also look at the valence electrons. Then also we will get Cn minus because here the valence electron is 4. This will be 6. So 4 plus 6 will be 10. This will be 4 plus 5, then one more electron will add, so it will be still be 10. So you can either look at the valence electron or the total number of electrons. For like if we have something like some big molecule like NH3, NH3 is not big, but still let me say that NH3 is a big molecule. I can't calculate for all the including all the electrons. Then I can just look at the valence electron. That is possible. But here I am talking about what is the contribution of each ligand to the complex. So each neutral ligand will give 2 electrons. That is why I have given 2 into 2, 4 here. So there are 2 Cp and we don't know how much each Cp is giving. So X plus Y, we are giving one is X, one is Y because we don't know. So X plus Y plus 10 is equal to 18 and X plus Y is equal to 8, which means that from X and Y we should get 8. So X can be 3 and Y can be 5 because hapticity 1, 3, 5 are possible, right? So option A is the right answer. If both are 3, let's say both are 3, then it will be only 6, right? Then it won't be an 18 electron complex, right? Because this is a organometallic compound, it should be 18 electron. So to satisfy this, we need to have 3 and 5 here from this equation, right? X plus Y should be equal to 8. So there is only one option possible for that, eta 3 and eta 5. Yeah. So any other doubts? Huh. Okay. See. So the metal is surrounded by some ligand. Say, let's say it is some A. Then my incoming ligand is B. So already metal is having lot of ligands which are A, and in associative pathway, initially when B comes, it will come and attack directly here, and it will come and sit there, something like this. Then one A will leave, then it will be like this. This is associative pathway. In dissociative pathway, the metal is like this, M A A A, and when some incoming ligand is coming, it won't come and attack here. Instead, one ligand will first leave. So it is like this. So there is a vacant space here. Then this B will come here. Then we have something like this. This is dissociative pathway. This generally happens when we have lot of crowding. For example, we have an octahedral complex. Then incoming ligand will find so much steric hindrance here, like if it has to come directly. So in that case, first one will leave, then we can, then this B will come and attack here. That so it generally depends on the coordination number. If it is too high, the coordination number is already like large, there is so much steric hindrance, then dissociative pathway will happen. Otherwise, this associative pathway. For example, for this square planar complexes, associative can happen easily because there is so much space on above and below the plane. Associative can happen like this. It can come and attack here, then the other one can be. Okay. So, any more doubts? Okay. Okay, we'll see in next class. Bye. Good night.